This lecture starts our study of Gaussian random variables. Gaussian random variables are perhaps the most important class of continuous random variables. Another name for Gaussian random variables is normal. And they're called normal random variables. It's a synonym for Gaussian. And, they're called normal because when you collect random data, Gaussian random variables are what you normally observe. The PDF of a Gaussian random variable looks a little bit complicated. It has two parameters, mu, which can be appearing here, which can be any parameter, and sigma squared appearing here and here, which has to be strictly greater than 0. To understand how this PDF works, right, it's helpful to remember to think about how the function x minus mu looks. It looks like a parabola. It goes to 0 at x equals mu. And then from there, you know that e to the minus something gets smaller as the something gets bigger. So in fact, at mu, the Gaussian PDF is maximum, and then it falls off and goes to 0 as x minus mu squared gets large. And it's symmetric around around x equals mu. Although my drawing isn't very good, this is commonly called the bell curve. Just as you should expect, the parameters mu and sigma are the expected value and the standard deviation. That is, E of x is equal to mu, and the variance of x is equal to sigma squared. Showing that the area under the curve here is equal to 1 is not so simple. You have to show that the following integral, 1 over root 2 pi sigma squared e to the minus x minus mu squared to sigma squared from minus infinity to infinity equals 1. To show this involves a couple of tricky steps. The steps are outlined in problem 4.6.13 if you're interested. Because the area under a PDF is always equal to 1, the shape of the Gaussian PDF depends strongly on the standard deviation sigma. In this figure, we plot a pair of Gaussian PDFs. On the left, we have a Gaussian where the mean is mu equals 2, but the standard deviation is sigma is 1/2. In this case, the PDF is very tall, but narrow. On the right, we have the same expected value, mu equals 2, but in this case, sigma is equal to 2. It's 4 times bigger. And this does two things. One, it spreads out the PDF to be much wider and broader, but because the PDF on the right has the same total area under the curve, in both cases that's 1, right? It has to be much, much lower. Keep in mind that the peak value of a CDF is 1 over square root 2 pi sigma squared. So when sigma is 4 times bigger, the peak value has to be 4 times lower. So on the left, the peak value is very close to 0.8. On the right, the peak value is close to 0.2. When we defined the Gaussian PDF, we asserted that the expected value was mu and that the variance was sigma squared. But to show that these facts are true is not so easy. So for example, if we want to show that the expected value is mu, we evaluate the integral e of x minus mu. which is equal to the integral minus infinity to infinity, x minus mu, 1 over root 2 pi squared, e to the minus x minus mu squared over 2 sigma squared, dx, with limits minus infinity to infinity. With the substitution z equal to x minus mu over sigma, we obtain e of x minus mu is equal to 1 over square root of 2 pi integral minus infinity to infinity z e to the minus z squared over 2 and dz. You can in fact solve this integral because z here is the derivative of z squared at the exponent. But in fact, you don't even need to do that step. What you need to realize is that z is an odd function, reversely symmetric around the origin, and e to the minus z squared over 2 is an even function, and the product of an even function and an odd function is an odd function, and the integral of the odd function over minus infinity to infinity is 0. Essentially, the integral from minus infinity to 0 cancels out the integral from 0 to infinity. So far, we may have given the impression that each Gaussian random variable with a different mu and sigma is different, but in fact, they're all really the same. If we start with a Gaussian x, which has parameters mu and sigma, right? It has PDF 1 over square root 2 pi sigma squared e to the minus x minus mu squared over 2 sigma squared. When mu is 0 and sigma is equal to 1, this simplifies to 1 over 2 pi e to the minus x squared over 2. And this particular version of the Gaussian PDF is so important that we call it the standard normal random variable. And typically we use the letter z to denote it. So z typically is the Gaussian 0, 1 random variable, and fz of z is 1 over 2 pi e to the minus z squared over 2. At this point, you might ask yourself, well, what is the Gaussian CDF? So since z is the simplest Gaussian random variable, maybe we can try to find its CDF. To do so, we write the CDF of z, which is the probability random variable z is less than or equal to little z, is the integral from minus infinity to z of the Gaussian PDF. And this we can write in the following form: minus infinity to z e to the minus u squared over 2 du. This integral looks pretty simple, but in fact, no matter what you do, whether you try integration by parts or some kind of tricky substitution, it can't be simplified. So instead, we give this integral a name. We call it the Phi function. It's phi of z. Phi of z is the CDF of the Gaussian random variable with mean 0 and variance 1. And you'd think, oh, we'll have to derive some kind of a phi function for each Gaussian with some mean mu and variance sigma squared. But in fact, we'll be able to represent all the other Gaussian CDFs in terms of this phi function. So just to repeat, This integral phi of z is the CDF of the standard normal mean 0 variance 1 Gaussian random variable. In the textbook, there's a table in which phi of z has been numerically evaluated. It starts, for example, at z equals 0, phi of z is 1/2. And other values of interest that you may want to remember, for instance, are phi of 1 is about 0.84. By the time you get to phi of 2, you're at 0.977. For some reason, this copy of the table circled z is at 0.5. I'm not sure why that's. You'll notice that the table starts at z equals 0 and goes up to z is 2.99. At that point, phi of z is pretty close to 1. Maybe you'll wonder, well, what about negative z's? There's a trick for using the table for negative z's that we'll discuss in the next slide. So for each value of z, phi of z is the area under the PDF integrated from minus infinity up to z. So it's the area in the left figure shown in the stripe. For instance, when z is 0, it's exactly the left half of the Gaussian PDF. And by symmetry, that value is a half because the area under the curve is 1, and this is the left half of it. This same symmetry allows us to calculate phi of z for negative value of z's. So on the right, consider a value where z is positive, and we're looking to calculate phi of negative z. So in this case, we want to calculate this area, the area shown as the left stripe zone. So we observe from the symmetry of the Gaussian PDF that, that in fact it's the same as the area under the curve on the right. Right, but this area, because the area of the total area under the curve is equal to 1, then the area on the right has to be 1 minus phi of z. So we get the property that phi of negative z is equal to 1 minus phi of z for z greater than or equal to 0. Now that we have phi of z, we want to use the phi function in order to derive the CDF of an arbitrary Gaussian. This is what this next theorem 4.14 does. Given Gaussian random variable x with parameters mu and sigma, it allows us to calculate the CDF of x in terms of the phi function. The second part of the theorem is just our old way of calculating the probability x is in an interval by using it as the difference of the CDFs. For instance, based on the first part, this is fx of b, and this second part, the difference is the CDF of x at a. The key thing is to understand how we got this result for the CDF. So for an arbitrary Gaussian random variable x, the CDF of x is the probability x is less than or equal to x, which equals the integral of the PDF of x using a dummy variable v from minus infinity to x. When we plug in the PDF of x, we get 1 over square root 2 pi sigma squared integral minus infinity to x e to the minus v minus mu squared over 2 sigma squared dv. The next step is to make the variable substitution c equals v minus mu over sigma. And this gives us 1 over square root 2 pi sigma squared integral minus infinity to x minus mu over sigma e to the minus z squared over 2, and dv dz is equal to dv over sigma times sigma dz. So sigma and sigma squared square root in the denominator cancel out, and we obtain 1 over square root 2 pi integral minus infinity x minus mu over sigma e to the minus z squared over 2 dz, and this is exactly phi of x minus mu over sigma. So we have a proof of the theorem, but in fact something more general is actually happening here. And what's happening is that if x is Gaussian, then z, which is equal to x minus mu over sigma, is also Gaussian. Understanding and using this fact is the key to avoiding a lot of messy calculus and variable substitution. Going back to our table of phi values, we notice that it happens to end down here at phi equals 2.99. And you might wonder what happens if you need to calculate, say, phi of 3, phi of 4, or maybe even phi of 6. So the problem with these values is that even at phi at 2.99, phi is equal to 0.998. So phi of 3 is approximately 0.999, and phi of 4 is like 0.999, maybe another 9, and so on. And phi of 6 has a lot of 9s. And you might think that, oh, all of these numbers are pretty close to 1 and kind of almost the same. But in fact, we often in communication systems want to be able to calculate probabilities of error that are 6 or 7 nines. And we need to distinguish between 0.999 and 0.99999. To do this, we define something almost just like the phi function, but it's opposite, and we call this function the Q function. So for positive z, where z is the Gaussian 0, 1 random variable, the Q of z is the complementary CDF. It's equal to the integral of the Gaussian PDF from z up to infinity. And if you give this a moment's thought, this is equal to 1 minus the CDF of z, which is just 1 minus phi of z. However, it's helpful to have a table of the values of q of z for z much bigger than 0. So our textbooks includes a table for q of z that starts at z equals 3, right, and ends at z almost equal to 5, what we see is that q of 3 is 1.35 times 10 to the minus 3, and that's equal to 0.00135. Right, so we know that phi of z, phi of 3, is equal to 1 minus q of 3, and it's equal to 0.99865. Next, when we look at z equals 4, q of 4 is equal to 3.17 times 10 to the minus 5. And so phi of 4 is equal to 0.999. You can figure out what the other digits are, right? But the important thing is that while phi of 4 looks like it's approximately the same as phi of 3, right? Q of 4 is 2 orders of magnitude smaller than Q of 3. In a communication system, 2 orders of magnitude means a lot. For example, if you send n equals 1 million bits, right? And the probability of error is equal to p equal to q of 3, then the number of bit errors a random variable k is binomial np. And if p is equal to q of 3, then the expected number of bit errors is np, and that's equal to 10 to the 6th times q of 3. It's equal to 10 to the 6th times 1.35 times 10 to the minus 3. It's 1,350 bit errors. On the other hand, if the probability of error is p equal to q4, then the expected number of bit errors, it's still np, but now when p is 10 to the 6th times 3.17 times 10 to the minus 5, it's only 31.7 errors. That's a lot less, and it may be the difference between a coding scheme being able to correct the errors and not. Since this lecture isn't subject to the usual 80-minute time constraint, my suggestion is that at this point you stop and go and do quiz 4.6 and solve these problems, and I'll take a break here and I'll come back and finish the lecture by working out the quiz solution.